Hey everyone, in this video we're going to discuss the performance characteristics and applications of PID control. And this content comes from chapters 7 and 8 of Chemical and Bioprocess Control by Riggs. This is going to be the first of a two-part video series. Okay, so in these chapters we're going to talk about various aspects of PID control. So our overall objective is going to be to set the controller. So we are going to determine what or learn how to set controllers, and what this means is the proportional, integral, and derivative terms within a PID controller. And also what we'll need to do is we'll discuss the selection of reverse and direct action controllers based on stability. And the overall objective is to determine what the controller settings need to be in order to achieve the desired level of control or control performance. Now this could be aggressive control, conservative control, minimum error between the set point and the control variable. I mean, there's various things that we'll discuss with respect to controller performance. Okay, so in these chapters, essentially what we're going to do is we're going to introduce the PID algorithm. So again, the PID algorithm is something that was developed by mathematicians in order to achieve a specific type of feedback control. We're going to discuss from the PID algorithm, we're going to discuss the transfer function. So we're going to derive the transfer function for the controller. And then also what we're going to do is we're going to look at the effect of this transfer function of the controller, so the transfer function of the controller, on the transfer function of the closed loop with respect to the overall response and stability. Similar to what we did previously for open loop processes that involved either first, second, or higher order processes. Okay, so some of the terms that we need to know, the P, I, and D. P it stands for proportional. Proportional. So in terms of controller action, there is proportional, integral, and derivative action. So for the proportional action, the controller setting of importance is going to be the gain, which is Kc. I stands for integral. So part of the control is going to come from what's called integral action. And the term for the integral action is going to be the reset time, or tau I. And then D stands for derivative. And so the derivative term is going to be tau D, which is the derivative time constant. Right, and as I said, we're also going to discuss reverse direct action on the controller. All right, so shown here is a little bit review of a block diagram of a typical feedback control loop. So starting now, going forward, we're going to primarily be focused on feedback control. So we're going to have what's called closed loop processes. Previously, when we had an open loop process, we were starting from right here, where we would change something like F specified. So we would change the actuator setting, and then the actuator would affect the process. The process would affect the control variable. The control variable would be sensed, and we would have some sort of sense signal. So we were going from the specified value to the actuator to the sensor. And this is this was an open loop process because there was no feedback. What we're doing here is we're now closing the loop. Right? By closing the loop, what that means is that now the sense value from the sensor is going to be compared to a set point. So instead of changing the actuator, now our input is going to be a set point to the control variable. Right? So we care about the control variable coming out of the process. We're going to have a set point, and so this set point is going to be compared to a sense value, and it's going to give us an error. So what we need to look at first is the controller algorithm. So what the controller is going to do is the controller is going to take the error and it's going to determine how to change the input to the actuator in order to get our control variable at our set point. Okay, so that's the objective. And so essentially we need to think about the controller is going to work to get it there. It's going to change by a certain amount, and it's going to change at a certain rate. So how fast and how much is what the controller is going to tell the actuator what to do. So previously, we have looked at these things. We looked at the transfer function for the actuator, the transfer function for the process, The transfer function for the disturbance, this is similar to the process, right? It's just a relationship between how a disturbance, which is a non-controlled parameter, affects the control variable. Again, we don't really need to worry about this so much because, again, regardless of how the control variable changes, this is going to be sensed. And all the controller can do is change the actuator. So whatever is affecting the process, the controller is going to account for by changing the actuator to get us back to the set point. Okay, so we talked about this before. In general, if we want to just derive the transfer function, so if we want to derive the transfer function for a closed loop process, previously in this class, we showed that the transfer function is essentially going to be the product. So the transfer function for a closed loop process is going to be the product of the transfer functions from the input to the output. And this is just sort of my terminology, divided by 1 plus the product of the transfer functions of the loop. Okay, so again, if we're looking at the transfer function, if we want to know the transfer function for essentially the disturbance, so for example, transfer function closed loop with respect to the disturbance, right? This is in the Laplace domain. This is going to be essentially the output, which is y, over the input, which is disturbance. Okay, so input to the output, so the transfer function from the input to the output is shown here. Right, so this is just going to be GD, transfer function of the disturbance, over 1 plus the product of the transfer function of the loop. So the loop is shown here. So the product of the transfer function of the loop is going to be GC, GA, GP times GS. Right, and so in order to derive this, in order to determine stability, we have to, or the stability response, etc., of the overall closed loop process here, we need to know all of these individual transfer functions. And we kind of know these. So we need to have these transfer functions and then again, rearrange, put into standard form, and then we can assess stability. Okay, what I want you to do, I'm going to pause on the side, is derive. So my question for you, you should be able to do this, is derive the transfer function for the overall process with respect to the set point changes. Okay, what this means is that, again, output is y, this is what we care about, our control variable, over y specified in the Laplace domain. Okay, so this is something that you should be able to do based on what we just did before. And now, once we know the forms of these, we're going to do some math on them, and we'll do a couple examples going forward. All right, so here's the results of those things. So when we look at the one that I just asked you to do, ys over y specified is, this is the product of the transfer function from the input to the output over 1 plus the loop. And the same thing for with respect to disturbances. So what you can see is that the bottom, the denominator of the transfer function is the same for each one, because for feedback control loops, they're essentially going to respond the same way. Their dynamics, their response is going to be similar. But the transfer functions of these of the numerator can affect, they can affect some elements of the response, but not necessarily not the dynamics or the stability. So because the denominator is what determines the general stability and response, we use this to assess general behavior. And the denominator, we call this the characteristic equation. But more specifically, we take the denominator, we set it equal to 0 and call this the characteristic equation. And then we can assess the stability like we did previously by looking at the roots or the poles. Okay, so again, the denominator of the transfer function is identical for both systems. Just to introduce a little bit more terminology, when we do things like set point tracking, servo control, right, this is where we're looking at, so the transfer function for set point tracking or servo control. This is what we did for the output ys over input y specified s. Right, so these are sort of interchangeable terms, or we can also have regulatory control. Regulatory control is, again, this is the transfer function where we have the output over with respect to disturbances. So in terms of regulatory control, the process will be running, disturbances will affect it, and then the controller is just going to adjust the actuator based on changes that are experienced based on disturbances. Whereas in servo control, we're applying set point changes and looking at how the process responds or how quickly it responds to set point changes. All right, so again, the denominator of these two is going to be the same. So we can look at the roots or the poles of the denominator to determine the dynamic characteristics. And again, this is going to be things like stability, in general behavior, like does it oscillate, how much the oscillations are, etc. Similar to what we looked at previously when we were just assessing the general dynamic behavior of transfer functions in general. Right now we just have a little bit more elaborate transfer function, but again we do the same sort of work and we can assess the stability the same exact way. Okay, so I'm going to start by introducing the position form of the PID algorithm. So the positional form of the PID algorithm, again, it's just the controller as a function of time. So remember, when we do transfer functions, we work in terms of deviation variables. So deviation variables means, a change from the initial condition. So we had, essentially the time domain form of the process, of the actuator, etc. And we went to deviation variable, subtract a steady state, and then looked at the transfer function, which is deviation from steady state conditions. So again, there's two ways we can express the position form. One of them is called reverse acting. One of them is called direct acting. We'll just introduce this one first. So the controller as a function of time equals, so C as a function of time equals the starting point. Okay, so it's going to be the starting point plus a couple terms. So there's three terms. The first term is going to be P, second term is going to be I, the third term is going to be D. So the first term, what you can see, is it's just going to be this term Kc, which is the gain, which is a proportionality constant. So the first term is just the gain times the error, right? And so what this means is that from this first term, the controller is going to change based on what the current error is. So it's going to be the change from the proportional term is proportional to the error. Surprise, surprise, right? Okay, the second term is going to be the gain divided by tau I times the integral of the error over time. So the second term, it's going to be the integral of the error from which essentially the controller was turned on. Okay, so we integrate the error over the whole time. And the purpose of the integral term is it's trying to keep the overall integrated error equal to 0, right? And we'll see some implications of this a little bit later. So again, this is the integral term. It's related to the integral error from the time we started. And again, this could be any arbitrary time the controller was turned on, or any time that the integral term was reset, for example. And then the last term is called the derivative term. So it's going to be, again, Kc times tau d times the derivative of the error. So at a specific point in time, the error could be changing. So if the error is changing, then the derivative term will become important. If we have a constant error, this term will be 0 and it won't affect the algorithm. Okay, so in this term right here, this is called reverse acting, and it's called reverse acting because C moves in the opposite direction as YS. Okay? To see what that means a little bit, like let's imagine, let's say, for example, if YS increases, okay, if YS increases and the set point doesn't change, okay, so remember the error is a function of time equals Y specified minus YS. Okay, so if YS increases, that means our error is going to be negative. Okay, so if the error is negative, all right, so if we're taking a negative error, right, this is going to be a negative term, we're taking C naught plus a negative term, that means C of t is going to decrease. Right, so what this means is that for an increase in the sense value, if the measured value increases, the controller is going to decrease, right? So that essentially what that means is the controller is reverse acting because it's moving in the opposite direction as a sense error. Okay, so direct acting, again, this in the opposite, essentially the opposite would flow. So we just change the sign of this right here. And again, if we change the sign in front of the gain, an increase in sensor value would cause an increase in the controller. All right, so essentially the point of reverse versus direct acting is just setting the sign on this gain term. So we're changing the sign of the gain. We're telling the process to go up or down. Right, this is going to be important because if we have a process where we increase the flow to the actuator and the process decreases, that's going to be very different than a process where we increase the flow to the actuator and the control variable actually increases, right? Either of those cases, we're going to have the controller work one way versus another way. All right, this next term just, again, defines the definition of the terms that we've already discussed. Okay, so from the previous slide, I showed I showed you the general form, the position form of the PID algorithm. We can go through and derive the transfer function for the controller like we did previously. Some of the things that we did, remember the first thing that we did is we went to deviation variable. And to put things in deviation variable, we just defined C equals C. We defined, okay, deviation variable, we defined C equals C minus C bar. We also defined the error equals E minus E bar. So we do this for our output. So again, for the controller, the error is the input, the controller value is the output. We also know that E equals Y specified minus Y. We can define E bar to be Y specified bar minus Y bar. And again, we know this is going to be 0 because at the steady state condition, this is initially 0. Okay, so after we do deviation variables, we substitute. Next, we subtract out steady state. Next thing we do is we apply Laplace. Then we rearrange. And when we rearrange, we get the transfer function for the controller that looks like this. So this would be a good activity here. Pause this. Make sure you can run through this process. You can look over the additional notes that I post on Canvas to work through the problem. I don't want to spend a lot of time doing this because we've done this a little bit previously. I just want to move into looking at the effect of the different actions on the controller performance. Okay, so the first thing that we're going to do is we're going to look at the effect of proportional action on the controller. And I think what I'm going to do here is I'm going to pause. Insert a new slide, and let's start here. So we're going to look at the effect of the proportional action on just the proportional action only on the controller response for a closed loop feedback system. Okay, in order to do this, right, so we're going to define our controller, right? Our controller is, for P only controller, the general form is K is C naught plus KC times E of T. If we derive the transfer function for the controller based on this algorithm alone, again, only P only controller, go through the work, we're going to see the transfer function equals KC. Again, the other terms are 0. So we're going to look at a system where, in this case, we're going to apply it to a first order process. So we'll say the process is Kp over tau ps plus 1. For here, we're just going to say the fast actuator and a fast sensor, so we're going to set these equal to 1. And so here we're just trying to take a general process and look at the effect of the P-only controller on the overall process response. Okay, so we're going to do this by, again, this is how we do it every time. We're going to look at the closed loop feedback, the closed loop transfer function, the transfer function for a closed loop feedback process. Right, this is for set point tracking, ys over y specified. Again, we could do it for regulatory control, which is the disturbance, but again, it doesn't matter because all we care about is the characteristic equation, which is what's in the denominator. Okay, so again, we know this is going to be input to output, which is GC, GA, GP. over 1 plus the transfer function of the loop, which is GC, GA, GP times GS. Okay, so now I got to substitute some things in here. So we know GA is equal to 1, GC equals KC, GP equals KP over tau PS plus 1. Okay, on the bottom we have 1 plus. Again, GA, GS, these are both going to be 1. And then we have the same thing, KC times KP over tau PS plus 1. Okay, so now in order to assess the stability, we have to put this in standard form. This isn't in standard form because it needs to be in a polynomial form. So what we're going to need to do is essentially get rid of the denominator and the denominator. So we can do that by essentially multiplying everything by 1, or I'm going to multiply the top and bottom by tau p plus 1 over tau p plus 1. Okay, so on the top, these terms are going to cancel off. On the bottom, this is going to cancel off with this term, and then this is going to be multiplied by this term. So again, closed loop. On the top, we have KC, KP. On the bottom, we have the tau PS plus 1. This is multiplied by 1, plus this term over here, plus KC, KP. Again, we're still not in standard form because we need to have a polynomial that has a 1 as a constant. And on the bottom right here, we have 1 plus KC, KP as a constant. So again, I'm just going to multiply this whole thing by 1. And instead of that, I'm going to do 1 over 1 plus KC, KP. On the bottom, multiply it by 1 over KC, KP. All right, so this is going to give us now the final transfer function. So on the top, we have KC, KP over 1 plus KC, KP. And then on the bottom, we have tau p over KC, right, this should be over here, 1 plus KC, please. So on the bottom we have KC, KP, tau p over 1 plus KC, KP times S plus 1. Okay, so now this is standard form where we have on the bottom we have our S terms and then we have the 1 as our constant. So if we look at this, we can see a couple things. So this right here on the top, this is our effective gain, Kc prime. So this is our gain of the loop. And down here we can see this is our tau p. All right, one thing that we noticed, this top part right here, assuming Kc is, these are all positive numbers, this term right here is always going to be less than 1. So for p-only control applied to a first order process, and really applied to any process, the gain will always be less than 1. What that means is that if we ask for the process to change by 5, it's going to change by less than 5. So there will always be some offset. So one of the consequences or one of the negatives about p-only control is that you can't actually get to the new set point. And the reason why you can is shown here mathematically. We can see here though, now tau p prime, this is always going to be less than tau p because the denominator down here is always going to be greater than 1. Okay, because these are going to be these are positive terms. Kc, this term has to be positive for stability. So tau is always going to be less than tau p. So what you see is by adding the gain term, it makes the time constant for response faster. So the effect of, and we talk in general, the effect of the gain on the feedback control is there's going to be offset if it's p only by itself, and the increases the response time, or it decreases the time constant of the feedback loop, which means response faster. So this is shown here graphically. These right here are values for Kc. So what you can see is that if we, for a general process here, a nominal value of Kc equals 1, the process is going to change to the steady state, but the change is going to be fairly slow. As we increase Kc, right from the last slide, a higher value of Kc causes this to be less, so it's going to change faster. And again, a higher value of Kc causes this to be closer to 1. So as you increase Kc, the time to get to the new, essentially the new effective steady state, or where it's going to be with the offset, decreases, or the time decreases, and the offset itself also decreases. Okay, so you might look at this and say, okay, we can use on an ideal first order process, we can use a P-only controller, and we just set it equal to infinity, and we get a good response. Yeah, that would work if it were an ideal process, but the reality is there's no such thing as an ideal first order process. Most processes are going to be higher than first order, or most processes are going to have some dead time, and what the dead time is going to do is it's going to lead to instability. So we're going to see that we have things like we get this quicker response, but at some point we're going to start to add oscillations. Okay, but the point is that if you have an ideal process, first order, you only need P-only with an infinite gain, but you're just not going to come across that. Again, so here this slide's maybe a little bit tougher to understand, but this is showing the proportional action of, this is the proportional action part of a PID controller response. Okay, so again, imagine here we have a PI controller, which we haven't discussed yet. So if we have a PI controller, what we're looking at right here is this is the change in set point, y specified. Okay, so if we did a step point change to a new set point, right? This shows the control variable response. So initially the control variable started to change quickly, it overshot a little bit, came back down, and eventually steadied out. Okay, if we break this down, now we can take this overall response right here, and we can break it down into C proportional, so the action that comes from the proportional term, plus C integral, the action that comes from the integral term. So the proportional term is going to be the highest when there's the largest difference. So the action of the proportional term should be highest initially. We also know that the action of the integral term, right, it should be higher, relatively speaking, it should be higher right here, but higher in a negative direction, which is shown right here. And then again, so you can see it kind of follows these oscillations a little bit. So again, initially there's a lot of error, so the proportional term is really high. As we approach the new steady state, at this point there's no difference, so the proportional action becomes 0. Right? As we overshoot, the proportional term kind of kicks in again as it gets down here at 0, and you can kind of see how it works. Now you can kind of tell that the integral, if we wanted to just look at this right here, the integral term would be responsible for us to get to this new set point. So the integral action part would probably look something like that. We'll come back to that later. Okay, so here we're going to look at the dynamic behavior of a P-only controller applied to a continuous stir thermal mixer. And some of the characteristics are shown here. This would be a good time to pause the video and go through and try to derive it yourself, and then I'll work through this. Remember, you only need to use the characteristic equation. Okay, so let's do that. I'm going to take the characteristic equation. So the characteristic equation for this process is GC, GC, GA, GP, GS plus 1. And what are we told? We're told the process has a Kp and a tau p of 60. So that means the first order process. The temperature sensor has a gain, or has a time constant of 20 seconds, and tau a is assumed to be small. So the actuator is supposed to be small, which means that GA is going to be 1. That means it's a fast actuator if it has a small time constant. And then again, because we're using a P-only controller, we're given GC for the controller is equal to Kc. Okay, so I want to substitute these into the characteristic equation. So GC is Kc, GP is equal to 1 over 60S plus 1. And then for the sensor, the gain on the sensor is 1 over 20S plus 1. Plus 1 equals 0. Here's our characteristic equation. So essentially what I need to do is convert this to polynomial form, and then look at look at the roots, or look at the behavior of the system. Okay, so to get this down to get this into polynomial form, I need to multiply everything through by 60s plus 1 times 20s plus 1. And if I do that, I get Kc, and then these terms will cancel off right here, plus, essentially now I have 20s plus 1, 60s plus 1 times 20s plus 1. Okay, and I'm just going to kind of multiply that through. So 1 1200 s squared plus 20s, 60s, 80s plus 1. So again, when I multiply the whole thing by this polynomial, it cancels off in the first term, and then I multiply this 1 by these terms, and I end up getting this equals 0. Okay, so now I'm going to maybe rearrange this a little bit. Again, I need to put it into standard form. My constant that I have right here is 1 plus kc, so I need to divide everything through by 1 plus kc. If I do that, I have 1200 over 1 plus kc s squared plus 80 over 1 plus kc s plus 1 equals 0. Okay, so now here is in standard form. So again, I can assess the general stability from this characteristic. Okay, so I can get, so what I know is that the general form for second order process is I have tau p squared s squared plus 2 tau p zeta s plus 1. Right, this is standard form for second order, so I'm going to use that. I'm going to use that form to look at this. So I know now that my tau p prime for my closed loop feedback process is square root of 1200 over 1 plus kc. Okay, so that's what this is what the time constant was going to be. So for this second order process, we can get, if we know kc, we can just put it in here, get the time constant. And then I also know that zeta, and again, I'm equating this right here, 2 tau p zeta equals 80 divided by 1 plus kc. If I do that, right, this right here is, so essentially, right, zeta prime, yeah, I'll be calculating zeta prime from this. So zeta prime is going to be, you know, if you do the math for that and you solve for zeta prime, it's going to be 1.5 over 1 plus, or square root of 1 plus kc. Right, so from here, I can determine what the oscillations are. One thing that we want to notice is that because kc is set to be a positive number, all these terms are positive, so this will always be stable. Right, so if we want to discuss just general stability, this is always going to be stable. If we want to discuss what values of kc will have oscillations, we know that when this value right here, right, when zeta prime is less than 1, it's going to have oscillations. If I increase kc from 0, this would be 1, right, so that's going to be stable, up to infinity at some point, right, this is going to become a really big number. So this zeta prime is never going to be less than 0, which means the process will always be stable. But we'll have oscillations at some point. Right? Once this zeta prime is less than 1, then I'm going to start to have oscillations. As you continue to increase the value of kc, this term is going to get smaller, therefore the oscillations will get bigger. Right? So in general, what we see is that as you increase the value of kc, the process responds faster, but then it starts having more and more oscillations. For a real process that has dead time and higher order processes, eventually, as you increase the kc, the process is going to become unstable because of the dead time and the other some other characteristics. But we're not going to go through the math for, you know, dead time type models. But notice that, again, this is an ideal second order process. You can make kc as high as possible. At most, you're going to run into a overly ringing type of a system. So, question for you is, what value of kc causes oscillations? Okay, so generally, so this slide right here talks generally about P-only control, and now we're gonna switch over a little bit to a real process. Okay, I showed you for some ideal processes, and so you can kind of maybe use your imagination a little bit and predict what would happen in a real process. What we showed is that for the previous example, as we go from a low value of kc, low kc, we had an overdamped process, right? In this case, when kc is 0, the value of zeta was equal to 1.15, right? So that would be overdamped, no oscillations. As we increase kc, at some point we're going to get this numerator or denominator equal to 1.15 when the zeta prime will be equal to 1, and at that point you have critically damped. Once zeta oscillatory zeta is less than 1. Once zeta is less than 1, which would be higher Kc, we're going to have oscillations. At some point when we continue to further increase Kc, there's going to be ringing. And then sustained oscillations, this would be where zeta equals 0. And then as you further increase Kc for non-ideal processes, and this could be processes that have dead time or lag, which really all processes have dead time plus lag. Right? We don't see this for ideal processes, but for processes that have dead time or lag, as you increase Kc, eventually you get into unstable oscillations, and then at some point, massively high values of Kc can just be unstable without oscillations, exponential growth. So that's the general progression as you increase Kc, and that's what you'll see as you look at some of the simulations that we have in this course. Okay, this plot right here shows graphically. Again, here we're looking at low Kc. General response, we have this is our set point change, right? So y specified, and this right here is y. So this is how y changes in response to y specified as you, again, increase Kc. I think in this example right here, maybe Kc was equal to 0.25. We'll just say here Kc was 0.35. You can see that less offset, faster response. Increase it to maybe, in this case, 1 or some value. This is now above, this is beyond critically damp, but it doesn't have any overshoot. You can see there starts to have oscillations that occur for the process. And then we have sort of ringing, so we have oscillations that don't damping out very fast. And in each case right here, if you look at it, as you further increase Kc, the amount, again, we want to look at the average distance, and here you can't quite see what the average is, but again, this distance right here, the offset, is going to decrease as you further increase Kc. I think here we go from 3 to 5 to 6, and then at some point we have, and again, this would be for a first order plus dead time model. And again, we don't go through the math for that, but you can maybe sort of see how that works because of with the math that we went for. For a first order process, we generally showed this right here. For a second order process, we showed that we can kind of go through this sort of progression, getting up to ringing, and then once you have the dead time model, which is more delay, it can become unstable, as shown here. This can also be expressed on a root locus plot. Again, these aren't terribly useful, so I'm going to skip forward again. It's just if it has real roots, if the real roots are positive, it's unstable. If the real roots are negative, all of these are stable. And again, if it has imaginary, it has oscillations. So this is generally what you can see from this plot here. We can also do things like plot the zeta. So here's the damping factor zeta as a function of Kc. And again, as you increase Kc, zeta goes from something greater than 1 to eventually it'll get to 1. The next thing it'll get to is 0. And then once it gets to a negative value, this is where we become unstable, right? And so here we're just looking at, we know zeta is greater than 1, it's overdamped. Zeta is less than 1, greater than 0, it's underdamped. And then once zeta is less than 0, it becomes unstable with oscillations. And again, you can sort of just see this. And this can show us a little bit about how we might select a value of Kc. Right? You can see that initially the damping factor changes by a little bit, and then it doesn't change by that much. So at some point, maybe we don't need a really large value of Kc. But we also want to see the effect of time constant because, again, the point of the gain is it affects the time constant, how fast the process responds. So we can plot the time constant as a function of gain. As you increase the gain, the time constant initially is going to come down a lot and then eventually steady out. Right, so here you can see there's a marginal improvement or marginal decrease in the time constant for values of 0.2 or of 2 to 7, but you see a really large enhancement from as you turn the gain on and increase it up to 2. Coming back here, you can see that there would be no reason to really come back here for decreased response time, so sort of the range over which the gains that are acceptable would be in this range. All right, so you can use these types of plots to determine, what are reasonable settings for the gain on the controller performance. Okay, so P-only control applied to a first order process without dead time. So without dead time, a pure or ideal first order process will always be stable, even with large Kc. But the combination always leads to some dynamics in dead time. So the first order without dead time is not a realistic model, so we can use that as an example, but we want to think about we want to understand the difference between ideal and non-ideal. But really it's the ideal is what we'll see, or the non-ideal we'll see through the simulation model, is that as you increase Kc, eventually things always become unstable because no process is ideal. Okay. One way that some controllers represent the gain is through the term which is called proportional band. So proportional band is just another way of saying gain in terms of a controller setting. You need to understand proportional band because some controllers that you might work on will have a setting of proportional band instead of gain. And so this works essentially exactly opposite. So I'll just kind of give you some definitions. So proportional band, PB for short, equals 100% divided by KCD. And this is like essentially a KC dimensionless term. I'm going to introduce another term, that's KC dimensionless. This is going to be Kc multiplied by delta ys over delta c. And I'm going to shade in these deltas because what this delta ys means is it means the range of ys. And what this delta c means, so this could be the span of the sensor, the range. And this delta c is essentially the controller output range. Okay, so basically, we can take whatever value of Kc, we can come up with a dimensionless value by multiplying it by the ratio of the ranges of the input and the output. The thing that's the main thing you need to understand, or you need to know, is that proportional band is inversely related to gain. So maybe I'll just put these two values together for one more relationship. So proportional band equals 100% divided by Kc, because remember Kc is just a setting, a controller setting, over delta C over delta Ys. These are inversely related. So as you increase the proportional band, you are decreasing the gain. You're making the process slower. As you decrease proportional band, you're increasing the gain. So we can look at how this works a little bit, or what is the kind of the general meaning of the proportional band. So maybe let's give you a couple more things to think about. So for generally for a large Kc, what that means, a large Kc means small change in sensor. So a small sensor change equals large actuator movement. So large actuator adjustment. Okay, so again, if the sensor is just changing by this much, the actuator is changing by a lot. What that means is that, so for a large Kc, the actuator can only move so much. Okay, so if a small change in sensor leads to a large change in the actuator, and the actuator can only change by this much, the amount of sensor range that we have is very limited, right? So that's essentially the band on our sensor that we can use is very small, which is why the proportional band is small. So high Kc means low proportional band because we can only use a small band of our sensor. Okay, inversely, again, if we have a small Kc, what that means is that a large sensor change equates to small actuator movement. Right, so in this case right here, we would be using, we can use the whole sensor range, but then we're only actually using maybe a fraction of the actuator component, right? So this right here is going to be maybe more conservative type control because the gain is small. And again, high proportional band because we're using all of the sensor, but limited in terms of the actuator movement. So an example for the proportional band and KC relationships is shown here. Again, I want to kind of draw a couple things over here on the side. So if we want to look over here and just kind of generally plot, if the KC, if the proportional, if the dimensionless gain was equal to 1, what that would mean is essentially we would be using on the pressure range for this example 0 to 200 psi, which is the maximum pressure range. And on the controller can use 0 to 100%. Right, so if the proportional band, if the dimensionless gain was equal to 1, we would have this kind of one-to-one matchup here. Right, so a high proportional band means we would be using less of the sensor, so essentially the controller would be larger. And for a small proportional band, we would be using, so a small proportional band, we would be using the opposite. Okay, so for this example, we have a pressure transmitter. The input signal goes 0 to 100 over 200 psi range. The control output range is shown here. Proportional band is set to 200%. Okay, so again, proportional band is set to 200%. So this is going to be, again, that's higher than 100. So that means, and they're inversely related. So it's a high proportional band, which means a relatively low gain. So this is going to be more conservative. Okay, so for this example, we calculate KC dimensionless. So KC dimensionless equals 100% to 100% divided by proportional band, which is 200%, which equals 1/2. And again, KC equals the dimensionless proportional band, 1/2 times the range of the controller, 100% over 200 psi, and this would give us 0.25% per psi. So for this proportional band of 200%, essentially what that means is that our controller range would have to be, and again we're going off the screen over there, from 0 to 100%, which is over there. And that means if we just kind of put this in the middle, I mean, we're losing half of it. So essentially we're looking at, here would be 50%, that would be divided by 4. So this right here would be 25, 50, 75, right? So we're only using on the controller 50% of the controller for the 200 psi sensor range, which means that in terms of our actuator, we're only really using half of the actuator movement for the controller. All right, so now let's look at properties of integral action. And so what we're going to do here is now we're going to use a controller algorithm that includes the proportional term we're just going to use the integral action of the term, which would be Kc over tau I. So there's no proportional term. We're not using the first term. We're strictly only using the second term, which is the integral of the error over time. Right, and so the transfer function for the controller, for this case, is going to be Kc over tau I, and then we have an S in the numerator. All right, so again, we're going to apply the I-only controller to a first-order process, and we're going to assume everything else is fast. So again, remember that G closed loop equals GA, or GC, GA, GP over 1 plus GC, GA, GP, GS. And again, actuator, we're going to say these are fast. We have these. Actuator and sensor are fast. And so this is going to give us GC, which is Kc over tau I S. GP, first order process, Kp over tau P S plus 1. Same thing on the bottom is we're going to have 1 plus, again, Kc over tau I S, Kp, tau P S plus 1. Okay, so now to get this to standard form is we have to multiply everything through by tau IS and tau PS plus 1. So our first algebra step is going to look like this. On the top we're going to have GC or KC, KP, And on the bottom, okay, multiply these things through. So this first term is going to be tau I, tau p s squared, plus second term is going to be, again, tau is times 1, tau is, and then the remaining over here is plus kc kp. And then the last thing we're going to do is divide. We need to get a 1 right here, so we need to divide the top and the bottom by kc kp. So on the top we have 1, and then on the bottom we have tau I, tau p over kc kp s squared plus tau I over kc kp plus 1. So this is our standard form of the closed loop transfer function for an I-only controller for a closed loop feedback process. What we see here for the integral action in terms of the offset, the gain is 1. So the integral term is what it guarantees that we have a gain of 1 for a feedback control process. So if we change the set point by 5, the process is going to change by 5 because of the integral term. And then now in terms of the dynamics, actually I'm missing an S right here. In terms of the dynamics, we can see tau I prime, or tau prime of the process is going to be square root of tau I, tau p, kc, kp. So again, as we this is tau p. Again, as we decrease tau I want to point out, make note of something up here a little bit. Offset's only 1. For tau I, see how tau I is in the denominator of this term? As we decrease tau I, we make the integral term stronger. Right? This term right here becomes bigger for smaller tau i's. So decreasing tau I is equivalent of saying increase integral action. So lower tau I means a more aggressive integral term. Higher tau I means less aggressive or more conservative on the tau I. So what this shows right here is that as we decrease tau I to make it more aggressive, it makes the time constant smaller, so it makes the process respond faster. Okay? Then also, we do the same thing we did previously, and we can look at zeta for this process, and zeta for this process is going to be 1/2 of square root tau I over tau p kc kp. Okay, again, so we see as you decrease tau I, so as we make the process more aggressive, the zeta becomes smaller. As zeta becomes smaller, it goes from overdamped to critically damped to oscillations. So again, more integral action or smaller tau I leads to more oscillations. Okay, so when we look at integral action, again, it's necessary. The point of integral action is to remove offset. Okay, the other way it affects the process dynamics and responses. It makes the process respond faster. More integral action means faster response. More integral action means more oscillations. And again, we get more integral action by decreasing tau I. Again, if we look at, we kind of went through this example before where we have a set point, change in set point. This is our overall process response for a PI controller. We showed what it looked like. We showed the controller. Previously, we looked at controller of the proportional. Proportional is just based on the error, just this difference. This term right here is going to be based on, this is the controller due to the integral. All right, so this one can actually change. And so what you can see is that this proportional term right here is what allows us to get the controller to get the step change in the control variable. Okay, so here's an example where we can go through the effect of a PI controller on a second order process. And so we'll go through that. Let's see, we have all the terms are shown here. So again, characteristic equation, PI controller, second order process. So again, we're just going to look at the denominator GA, GC, GP, GS plus 1. So we have second order process. We're going to assume that actuator and sensor are 1, and this is second order, and this is PI. Okay, so characteristic equation here is going to be, for a second order process, we have Kp, so 1 over tau p. So second order process is tau p squared, s squared, plus zeta is 2. So this next term is going to be 2 times zeta times tau p, which is 20 s plus 1. This is our second order process. Our PI controller is we have Kc here, tau I equals to 1, so we have Kc for the first term, and then the second term we have Kc divided by tau I, s, so 1 divided by 1 times s, plus 1. Okay, we rearrange this, put it in standard form, and then we get 25 s cubed plus 20 s squared plus 2s plus 1 equals 0. Okay, so here's standard form. What we can see is now we can use the Routh array criteria to determine stability if we want. But again, we know that for a second order or for a third order process, a third order polynomial process, it always has at least one root, right? So a third order polynomial can look like this, where it has 3 roots, or it can look something like this, where only one root goes through and it has imaginary roots. So we can determine the real root first and then factor it out. So the real root for this one that I determined by plotting it equals negative 0.764. If we wanted to, we could determine, we could factor it out, because this would be equal to the root of s plus 0.764, right? We can do polynomial division, 25 s cubed plus 20 s squared plus 2s plus 1, or you can use your calculator or some other mechanism to do this. If we do this, we can come up with our polynomial, and then we can look at the characteristics of the polynomial. I'm going to say, you pause this, go through this, remind yourself on how to do this polynomial long division. It's a good skill to know. Then you might have to put that into standard form, and if you do that, you can determine tau p for the second order process and zeta for the second order process. What you see here is that, again, it's going to be stable because these are both positive. This would have to be negative for it to be unstable, but this is going to be highly oscillatory. Because this zeta value is so close to 0. Okay? So again, we can use this to determine the process response. Now what also we can do is I can go back. I started this where I put a tau, I used tau I of 1. I could go back and I could start with a tau I right here, and then carry this tau I through. And then we can determine what values of tau I cause the process to go unstable. We can also determine what values of tau I cause the process to have oscillations, right? Just like what we did with Kc. Okay, so maybe we'll look at an example of that later. And point is, characteristic equation, we can determine the dynamics of the process. Based on understanding what some of these characteristics are, we can determine what values make the process go unstable or have oscillations or other types of dynamic behavior. Okay, so we know that both as we increase Kc, it causes the process to go from overdamped to underdamped which is oscillations, to unstable. And the same things that happens when we decrease tau I. So as we decrease tau I, it causes which is more integral action, it causes the process to do the same thing. So sometimes we might not be able to see or determine if there's too much or too little of one term or the other. So again, on the top, this is showing as we increase Kc, the process goes from overdamped to some oscillations to ringing. Same thing if we decrease tau I. Right here we have some oscillations more, and then eventually we're going to continue to get ringing or sustained oscillations. So we get the same effect by changing the terms. Increasing Kc has the same effect of decreasing tau I. Both of these, as we're going in this direction, lead to more of the respective action. So more proportional, more integral action, right? Because it's making the process more aggressive. Okay, so ideally we want to tune the controller such that there's the correct proportion and the correct amount of Kc and tau I. So ultimately what you want is you want your Kc to be as high as possible, but you also want tau I to be, you also need enough integral action so the process removes its offset quickly. Okay, and so we'll go through tuning criteria later, but for now we can get some general heuristics. Okay, so if Kc is too small relative to the ideal amount of Kc, the response will be slow. Okay, and again, if tau I is too large, so what this would mean is small integral action. What this means is offset removal will be slow, and oscillations won't occur around the set point. So ideally, we want to tune the controller such that we have fast response and fast offset removal, and that's kind of a delicate balance between those two parameters. So how do we know which one to change? Okay, we can, once we properly tune a controller, and we're going to do this in Chapter 9 coming up, and we'll go through a variety of tuning mechanisms, we'll come up with the right ratio between Kc and tau I. Okay, if we plot the controller output versus the control variable, or the sense value, so here's ys, and here's the controller output. The controller output should lag the sense value just a little bit. If it were proportional only action, these would line up perfectly. But the integral action is required to remove the offset, and integral action is going to cause there to be a little bit of a lag in the controller output relative to the sense value. So there should be a little bit of lag here. So with a properly tuned controller, if you plot the sense variable, so here's the data for the sense variable, versus how the controller is changing as a function of time over the same integral, you can collect this data and you can make a note of what this lag is. Okay, so you can determine from this if there's too much Kc or too little tau I, because again, if the lag is less, that means there's more proportional action than needed. If the lag is more, that means there's more integral action than needed, and you have to tune down the integral, right? But you need to have access to this, and which is why one of the important things to do when tuning a controller is to document changes and make a note of what your data looks like. As stated, when there's too much proportional action, the control or the see this again. This is output. This is input. Sense value. This affects the error. Error is the input for the controller output. There will be no lag in the output. This means there's too much proportional term, because again, the proportional term is doing all the work. The integral term is not doing enough work. If the lag is too small, that means that the integral is doing more work than needed because the delay is more sluggish, right? Now, in either the control performance could be acceptable. The point is that it's not ideal relative to your control objective if you're trying to minimize the amount of error or have a process behave a certain way. Okay, so I'm going to stop there for this video, and next time we'll pick up on properties of derivative action.